Hello everyone. In this video, we'll learn about tensors, what tensors are. So before we learn tensors, we must know what is a function. So function is just a map between a set, which is set x, to set y, and this is just a map. What is a vector? So if you think of vectors as just arrows with some magnitude and direction, that is just a representation. So these vectors belong to a much broader concept which we will call as vector space. So a vector space is a group, or more precisely, we say that a vector space is a known empty set which follows certain axioms, and it is defined over a field. Now, this field in physics we generally use a real field or a complex field, and this vector space it should have two definite rules or operations which are properly defined. One is the scalar multiplication, and the other is vector addition, and this vector addition is abelian. Now this vector space I denote with this circle. Let's say V is the vector space and small v is some element in this vector space. Now this is defined over a field I denote with capital F. Now what is a linear functional? A linear functional is anything which maps this vector or the elements of this vector space to an element or multiple elements of a field. So this I denote as G, which takes in V as a vector and maps it to alpha. Alpha is some element of a field. Okay, so these linear functionals are of course linear. So what do I mean by linear? So linear means that if this V, I denote it with the help of okay, so by linear what do I mean? So by linear I mean that if this V could be represented as sum of V1 plus V2, so this can be broken down into this format. So this is the linearity property of linear functional. Now these linear functionals, they also form a vector space which we will call as dual vector space. Dual vector space. Okay, so this is just the if you know somewhat quantum mechanics, so you might be knowing this is bracket notation, in which this is denoted as inner product of psi and phi. I'll not go in detail, but you can look up some quantum mechanics books in order to look for this. Okay, so now you know what is a vector space, what is a dual vector space. I must tell you that the elements of these vector space, I'll be calling them as vectors, and the elements of these dual vector space I'll call as dual vectors. So psi I am denoting as vectors in vector space, and sorry, phi I am taking as vectors in vector space, and psi is dual vector in dual vector space. Okay, now I would ask you, what is a tensor? So a tensor is just a multilinear map. Now what do I mean by multilinear? By multilinear, I mean that let's say I take a tensor, so it must be linear in all of its arguments. So let's say it has two arguments, psi and phi. I can write psi as psi1 plus psi2, let's assume, and phi as phi1 plus phi2. So I can write psi this t psi phi as this form, and I can expand it in this form. So this is the multilinearity property. Now it is a map. So what is it mapping? So it takes a tensor of type p comma q, takes in two things. It takes in uh, p copies of dual vectors which belong to dual vector space, of course, and q copies of vectors from vector space, and map it to field. Now for this case, for simplicity, we'll take our field to be real field, and we'll proceed as follows. Now I would ask you, what is a tensor of type 0, comma 1? So a tensor of type 0, comma 1 will take one vector. Now this vector is from vector space and map it to field. Now I would like to remind you that we were looking at linear functionals. So these are linear functionals. So a linear functional, what it does is it takes in a vector. So this is the vector, and maps it to field, and this alpha belongs to that field. Okay, so now we come to this definition. A tensor takes in a vector and maps it to a field. So this is a linear functional. I could say that this tensor is just a linear functional that's mapping a vector into a field. And these linear functional form a vector space which is dual vector space, and the elements of these dual vector space are dual vectors. So I can say that the linear functional is just that dual vector which maps a vector to field. Okay, now what is a tensor of type 1, comma 0? It takes in a dual vector and maps it to field. Now I told you that what is a dual of a vector space. What is a dual of the dual vector space? That is just this original vector space. Now this original vector space also has elements which we call as vectors. Now these vectors, I can define a linear functional on this dual vector space which maps the elements of this dual vector space to field, and those linear functionals are just the elements of this vector space. So I can call this tensor of type 1, comma 0 as that vector. More precisely, we call the elements which are dual vectors as covariant vectors. Covariant vectors, and the vectors as contravariant vectors. Okay, so now you know what is covariant and contravariant vectors. I would ask you, what is a tensor of type 0, 0? A tensor of type 0, 0 maps a real number to a real number, and that's a scalar. Okay, so now I would ask you, what is a tensor of type 2, 0, comma 2? It takes just two copies of vectors and maps it to real space, real field. Now we have taken field to be real, that's why we are saying it is mapping it to real field. It could be any kind of field. Okay, so this was the example. So let's say we have two vectors, and these vector belong to vector space. Now these vector, if we do a dot product, we get a real quantity which is a scalar, So this dot product that we have been doing since our undergrad, this is just a tensor of type 0, comma 2. So these tensors are more general way of representing what we call as scalars, vectors, and some higher order tensors. This is the generalization. So first we know what is a scalar, then we learn what is a tensor, and then we learn what is a higher order tensors. By higher order I mean whose rank is more than 1. So I can, for simplicity, we generally say that a tensor of rank 0 is a scalar, tensor of rank 1 is a vector, and tensor of rank 2 is we don't call them scalars and vectors, we generally call them tensors only, and so on. We can go on further. Now this I told that type of tensor, type p comma q, a tensor of type p comma q. Now there this type is just the rank. So rank tensor of rank p comma q is just the same thing as saying that a tensor of type p comma q. Okay, that's all for this video. I'll see you in the next one. Thank you.